Hello, Physics 135 students, and welcome back. This is the week 2 lecture. This is our third class. Today, we're going to start with an icebreaker. Actually, I'm not going to go quite into slideshow mode since I want to pop around to some different tabs later on. So first, for our icebreaker, the question is, what is your favorite breakfast food? Now, of course, if we were in person, we'd be able to chat with our neighbors. I'd be able to hear all of your responses to try to address that otherwise lack from this lecture recording. I'm going to ask that you all enter your favorite breakfast food over in the Discord. And I've set up a channel called Lecture Discussions for you to do so. And that's how you can, again, not only post your own response, but also take a look at what I wrote, where I waxed philosophic about pancakes and waffles, although admittedly, I mostly have oatmeal these mornings, which is maybe a little bit more healthy. I at least feel pretty good when I eat them, whereas these days I do feel a little bit bloated, I guess, with waffles and pancakes, even though they are still delicious. Okay. And it'd be great, by the way, if in addition to posting in the Discord, I didn't mention this here, but also please do email me your response. I guess I'll be in the Discord a little bit more than I had anticipated in terms of trying to get things nice and tidy. Um, but for the most part, I won't really look at what people post there. It's really more of to try to engender some discussion and help this become more of a community and rather than feeling isolated or siloed with this virtual class setting. Okay, and then for today, we're going into two real big topics. The first is the semester-long research project, and we'll do kind of a who, what, when, where, why, and go into a lot of the different details about your semester-long research project, which, a reminder, this is a major part of your grade in this class. It's 20% of your total grade. And then the second part of class is going into more about Greek astronomy. We'll have two different activities as well as some lecture. So the overall goal that I have generally is to try to make sure that at least 50% of classes are really active and dynamic and really student led, since physics education research shows that students come away with their understanding of the material, vastly improved when there are these tactile and really experiential learning activities or ingredients. Now, admittedly, the last time I taught this course in person, I think I did quite a good job of that. There's maybe a mixture of opinions about how students feel about flipped classroom or having a lot of active discussions. But nevertheless, that went really well for this class in person. For this online class, I can't structure it the same way. And as a result, I've been really creating these lecture materials wholesale. And similarly for the activities, a lot of them won't work so well. So some of them I have been able to recycle, but some classes, there might be more of a 90-ish% lecture component and 10% activity where kind of like the icebreaker, there's still like mini activities sprinkled through. But I will try to come up with as many activities as I can. Okay, and then moving on. So for the semester-long research project, the reason why we're doing this project is, admittedly, I have a bit of a bias towards research. I have been associated with research ever since I was a freshman in college, and honestly, I would have loved to have gotten involved in research in high school or maybe even earlier than that. I knew that I wanted to study the stars and the cosmos ever since I was like 10 years old. There just weren't really resources for me back then. It's a little bit of a different world these days, honestly. Now, in summary, I've been involved in a wide variety of research projects from undergrad through grad school during my postdoc. And really, I've supervised a number of research projects for students as young as seventh grade middle school students, a lot of high school students, quite a few undergraduate students, master's students, retired lawyers, medical doctors, etc. So everywhere from 11 to 77 in terms of quote unquote students' ages at this point. Nevertheless, in terms of my first authored peer-reviewed publications, I have four. And the reason why I'm emphasizing this point, despite my, at this point, I think pretty, involved research journey, I would say that I have 10 years of experience as a researcher. I only have four first authored publications. And to some extent, I could have, dumped a whole lot more time into research and less time playing hockey or learning how to play the ukulele, etc. But I like to have some balance in my life. And I also really enjoy teaching. Now, the other part of this, though, is just that it takes a lot of work and effort to come up with a publication. So, in terms of why a semester-long research project, your take-home message is there are really two reasons. One is that you're going to get a much deeper understanding of the material that you decide to research than we would otherwise be able to cover in this class. So that's number one, is being able to go deeper into a particular topic that you get to choose, as we'll talk about later. The second reason, though, is because, again, publications are not a simple thing to come by. You really need to have a lot of diligence and persistence in order to come up with a publishable product. Admittedly, your goal is not to reach the same sort of tier of professional grade research that I've had for my publications. But nevertheless, if you get a publication out of this, that could be a nice booster, whether that's for job applications or for grad school applications. Again, this is something that is pretty unique and would help you stand out, is my opinion. And that has been the case for the folks that I have mentored. Okay, so in terms of the semester-long research project, your overall goal is to complete a high-quality paper. Now, what do I mean by a high-quality paper? Really, what I mean is that you should aim for something that is publishable. Now, publishable specifically in an undergraduate journal. I do not expect, it would be really unreasonable for me to expect you to be able to publish your research in a professional grade journal. This is meant to be, a course project, and ultimately you do not have to publish in an undergraduate journal. But that is the criterion, that is the goal for this research project. And there were several students last semester I did the same project with, but for stars and galaxies instead of the first 3 minutes. There are several students who I did encourage to pursue publication for their work. So again, if you're one of those students, by the way, and you haven't shot for publication, I do still encourage it, as well as, of course, for this class this semester. All right, now in terms of this research project, now one thing that's kind of nice is that you get to choose the topic. Now, in terms of that choice of topic, it has to be relevant to this class, of course, but even kind of more importantly, it has to be scientific, right? It can't be something that's pseudoscience. So, in other words, you need to have a specific research question or hypothesis that you're trying to answer, and not like sociological or political science. I was a little bit more laissez-faire about that last semester. This semester, I really, really want this to be a scientific research project, since this is a physics class, even if it's an introductory physics class. And then the second point is that, of course, it has to be relevant to this course. Now, what do I mean by relevant? I have posted all of your reading assignments on Brightspace at this point. That doesn't mean that you have to go through and do all the reading assignments this week, but you can take a look at, especially for, say, some of the last reading assignments, like reading like R14 and R15, we end up going beyond the book, and I start suggesting that you take a look at sections of the OpenStax physics or OpenStax astronomy textbooks, and some of the stuff is really freaking cool. In my not so, mm, in my admittedly somewhat biased opinion, but there's some really interesting stuff that is totally unanswered, right? Like dark matter and dark energy, two of the biggest puzzles in the universe, and they're directly applicable to this course. So you could do a research paper related to dark matter, dark energy, for example, or really anything that is, covered in the readings or the lectures. But the lectures are by and large following the readings. And in some ways, I'm going to supplement. It's not going to be exactly the same as the readings. But by and large, these are going to cover the same topics. Okay, the other important aspect is that you can't just do something on like the Copernican revolution necessarily. You have to, or on like the Eratosthenes circumference of the Earth. Your research topic has to be something that is really an active area of research. So, what do I mean by an active area of research? The majority of your references should be from the last 5 years. In other words, from 2021 forwards. And really, this should say a vast majority. In other words, it's okay if you want to cite one of the historic articles in your field. If you're doing a research topic on gravitational waves, it'd be pretty cool and sensible to cite the 1960s paper that's kind of first started talking about gravitational waves, and that's perfectly acceptable. But the majority of your source material does still need to come from the last 5 years. Now, admittedly, this is a little bit more applicable for review articles compared to original research articles. Um, so regarding that distinction, for undergraduate journals, there are a variety of submissions that they accept. But for this class and for this project, the two most applicable are so-called original research, where you are discovering something for yourself. And none of the students in Stars and Galaxies went for this last semester, but we do have quite a few more physics majors here in the first 3 minutes. And so I'm hoping that at least one of you will opt for original research, but it's not required. You get a choice. So either original research or a review article where you're looking at what's been done before and there are two parts of this. One is you summarize what's been done before, but really importantly, you need to not just summarize, but synthesize and point out what are the unsolved puzzles that are still to be worked out. So again, you have choices here in terms of which type of research you want to pursue. And especially for the review, again, the majority of your references have to be recent, as in within 2021 plus. Okay. And then in terms of, again, the goal being to publish in or to write a article that is publishable in an undergraduate level journal, there are quite a few options. One of them, especially if you're considering original research, probably the best option would be Purdue University's own undergraduate research journal. So that I have a link to the different journals' websites, as we'll talk about. Now, this is only for original research, as far as I can tell. Maybe they'd accept a review article, but I don't think so. The other benefit is that I'm pretty sure it's no charge, or if you prefer, it's included with your tuition. So that part is nice, of course. Another option, which I otherwise really recommended and talked about last semester, is this Stanford Journal of Science, Technology, and Society called Intersect. They accepted a large variety of formats, so it would have been perfect also for review articles. Also nice that I'm pretty sure there was no charge, but they're not accepting new submissions. So I've included a link, and if they do change that at some point this semester, as far as I can tell, the reason why they're not accepting new submissions is because they got super backlogged and overwhelmed. Fair enough, maybe that's the downside of no charge and being open to everyone. Whereas our Purdue undergraduate research journal is only open for submissions by Purdue students. Now, okay, so there are those two options. We don't really have a review option yet. And there are some options out there, but they're pretty ouch. In particular, this American Journal of Student Research went up more than $100 from August of 2025. But they do accept review articles and really a variety. They have templates for different review article types. The narrative review is what I would best recommend. There is also Curio Academic, which recently rebranded to the Curio Review. They do accept both original research and reviews, but probably because of this rebrand, I think they mostly get reviews. And it's quite a bit more affordable, but I don't know about you, it still feels kind of like ouch. Last semester, I did set this up into being a little bit more of a competition where the top submission overall, I said I would pay the publication fee if it was reasonable, and the student opted for Curio Academic slash Curio Review. And this semester, I'm thinking, well, I do want to support you all to strive for excellent research, but $200 out of my pocket, I wish that that was, something I could be more blasé about. But unfortunately, I have to live with, economic realities, right? Like all of us do, and that's not super ideal for me, unfortunately. But in any case, so there are these two options, and um, basically because of this landscape of really not having an undergraduate level journal that accepts review articles but is free for students to publish in, um, last semester, just kind of like while I was eating dinner or like in spare moments here and there, I set up my own journal called the California Technical Journal and asked a friend if they'd be willing to serve as one of the um, editors and reviewer. Um, so this is still under wraps or still in development, I should say. In particular, the website is largely set up, but I don't have a backend server. So in other words, it cannot really accept responses, including like contact requests, etc. So the reason why I set this up was again because there's not really free undergraduate journals. Part of the reason why it's not functional yet, though, is well, one, I've been busy, of course. And then two is that towards the end of last semester, it was around December or so, that I found that, oh, there's this new journal that's called the Open Journal for Students and New Scientist Research. And this is hosted by University of Massachusetts Amherst. Just like for Stanford Intersect, I'm pretty sure this is free. Now, this was announced back in October 2025. I noticed it a few months later while I was working on still basically on the backend server for California Technical Journal. Um, Now, although it's been around for a few months, the last time I checked, they still don't have any publications. So I don't know for sure if this is an option or if it's kind of a pseudo option. They don't really have a lot of details as far as what they want, is the other thing. So I'm kind of in flux about whether California Technical Journal is something that I should still work on or whether it's superfluous at this point. And the name I'm not really super sure about, but I moved to California. I love the redwood trees and stuff, so that's part of the reason for the name there. Okay, and now we're going to do kind of a lecture pause because I would bet that there are more options out there. It took me a few months to realize that the University of Massachusetts Amherst Journal existed. So now I'm going to ask you all to pause this video and engage in this activity. I want you to look for some additional options yourself. And maybe you'll find something, maybe you won't. Either way, spend, a few minutes on Google or however you search for things, DuckDuckGo, etc., whatever you prefer. And please post in the Discord in the lecture discussions channel with a thread, which I'll talk about in a moment. But please also email me if you find anything. If you don't find anything, you can still email me. It's still nice to stay in contact with you all. And again, I created a thread. You don't actually have to use the threads. There's still a little bit of a newer concept for me personally. I think for my future Discord bot, like activity analysis, I think that threads are going to be a bit of a pain for that. So maybe I won't do that in the future, but for right now, I thought it'd be better organized that way. Okay. Remember, go ahead and pause the video now, work on this activity. Okay, unpause. So moving on, regarding the semester-long research project, I've decided to divvy this up into 4 deadlines. And the main reason for that is last semester I just had, all right, one submission at the very end worth 20% of the grade, and I was really disappointed, unfortunately, by the quality of the submissions, to the point where I gave students an opportunity to resubmit their paper. And so instead, I'm just kind of formalizing that, and I'm going to require some deadlines to avoid procrastination. So your first deadline is due in exactly 1 week from today, being January 25th, maybe a little bit later when you review this. So in other words, possibly due sooner for you all. So February 1st, which is Sunday, your topic, the type of your article, whether review or original research, and your target, which is again the undergraduate journal that you would plan to submit to, are going to be due. About a month later, your annotated bibliography will be due. And we'll talk in more detail about that in a future lecture. Probably not this week three's lecture number 4, or like overall class 4, but probably after February 1st. And then your third, about 1 month after that, your third submission deadline is March 29th, where you'll have half of your paper written. And then shortly before finals week uh, is the deadline for your final paper submission. And so this semester, I'm trying to break things up a little bit. You'll have your final paper due April 26th, and then you'll have your final exam during the actual final exam week. Okay, and so now we have actually another lecture pause. And this I do expect to take a somewhat significant effort. It does require some math. It's high school level math, but if you're not super familiar with trigonometry or basically pre-calculus, then you might have some trouble with this. And if you have trouble, that's totally okay. I'm going to really strongly suggest that you ask for help on the Discord. If you're doing well on this activity, it'd be great if you can also mention that on the Discord. If you're willing to help people out, that'd be really nice. And again, make this a little bit more of a community and really a nicer experience rather than being siloed and isolated. And of course, you can also attend my office hours, which I think I have to modify this week. I'll probably have them this Tuesday instead of on Thursday, or I think that they're actually on Wednesday this week. And then regarding this worksheet, though, let's just make sure that that part's clear. If we go to the bright space, and by the way, you might have a different view than me, but I always go to content, and then I have these like menu items here on the left. And then if I click on lectures, I have posted this Eratosthenes worksheet, and interesting as far as that upload order goes. Um, but I have uploaded in 3 different formats. The PDF version is probably not super helpful, but I've also posted a Word doc, which you can certainly upload to Google Drive and modify as a Google Doc. That's what I typically do. But I've also posted an ODT. This is Open Document, I guess, text format. And this is helpful in case you want to use, like if you're on Linux, for example, and you want to use one of the free, like LibreOffice software. And maybe it's helpful if you're just, if you have some other text editor, whether on Windows or Mac. So a couple of different formats, and this is where you can find that worksheet. So at this point, go ahead and pause the video. And I guess the last thing I'll say is that depending on, your background with math, this could take quite a little bit. The goal for this lecture is for it to be really like 1 week's worth of material. In other words, 2.5 hours in total. I'm projecting that this video will be about 1 hour. So there are 2 worksheets. I'm expecting you to spend the other hour and a half, roughly speaking, on those 2 worksheets. So anywhere from 30 to 60 minutes could be acceptable. It could be that you're faster. If you're faster, it'd be really great if you could help some people out in the Discord. And importantly, in the Discord, please do not post your actual worksheets there. Don't post your answers, but do feel free to chatter. And if you need to upload a diagram or something to show kind of what you mean, that's totally fine. The other thing about the Discord is there is a voice chat channel, and it is possible to like do video calls via Discord as well. So it's possible for you to not just be asynchronous, but to chat with each other synchronously additionally. Okay, so go ahead and pause the video and work on this worksheet. Okay, hopefully you paused the video and worked on the worksheet. Now we're going to unpause and move along. So next, we're going to talk about ancient Greek astronomy. And last class, I was asking for you all to give me some feedback on whether you liked the AI generated content or not, and I got crickets in response. So this time I did a little bit of both. Honestly, part of the reason is that I got like an AI response, and I didn't feel like doing 3 iterations or even more to get more of what I wanted. So I started with this, but we're really going to focus our time on the human version. But nevertheless, another kind of fun fact in terms of physics education research is actually also what just more broadly education or higher education research shows is that having multiple representations of the same material is helpful for student retention. So, in other words, although we're going to take a brief look at this AI version before the human version, there is a benefit from that. You get exposed to the material more than once, you're more likely to retain it. That's signaling to your brain that, oh, I've seen this before, it's familiar, it's easier for me to hook up my neurons and get that memorized. Now, one thing is that there are a couple of broken images for these AI generated slides. I do otherwise like the format and stuff. In some cases, I think the text is too small. In this case, it's okay, probably. I'll go full screen now to try to help with that a little bit. But we'll talk more about the Very Large Telescope. One thing I want to point out is that although the Very Large Telescope does use adaptive optics, and it was one of the first to do so, it is by no means unique in that capability today. Well, and what is adaptive optics? We'll talk about that when we have the human version with a working image. All right, and then you can see that this is a little bit dated. We have NASA's Hubble Space Telescope, definitely with contributions from ESA and a wide variety of international partners as well. But of course, Hubble Space Telescope is not the latest and greatest space telescope these days. And then rewinding, of course, to ancient Greek astronomy, or in other words, what astronomy was like about 2.5 millennia ago. Really, these ancient astronomers had to use their eyes and simple measurement tools. And really, they use their brain a lot, which is great. And part of the issues with AI is I have seen kind of the death of critical thinking in a lot of students. Although there are still a lot of students that have are part of La Resistance and are still using their brain, which is great. So, okay, back to ancient Greek astronomy. So last class we talked about how Thales of Miletus was one of really the first important scientists. He was the first to possibly come up with a prediction for an eclipse in what Isaac Asimov, a very famous and well-loved science fiction writer, declared the birth of science with that first eclipse event. About 2 decades later, we have Anaximenes, who was the first amongst the Greeks, at least, to point out that there were planets. The Chinese, or ancient Chinese at least, knew about this probably 2 millennia further ago, back in around 2000 or maybe closer to 3000 BC. Then Anaxagoras, who we called the first physicist, really started to not just describe events, but to give some physical understanding of the events and gave the suggestion that there's moonlight that's received on Earth, and that moonlight is ultimately reflected from reflected light that's coming from the sun. And then the Pythagoreans came up with this idea of circular orbits for the planets, and then Aristarchus a little bit later with a heliocentric theory. And in the human version, we'll extend this a little bit further. So again, you can see kind of a broken image here from the AI, which I didn't bother to fix. And we'll go ahead and gloss over, but Aristarchus is one of the most most pivotal, or in other words, most important ancient Greek astronomers in terms of coming up with the distances as well as sizes of the sun and moon. And really, the mathematics that was used was perfect. And there was a little bit of measurement error, but this idea about knowing that the sun was much, much larger than the size of the Earth was partly why Aristarchus supposed, as we'll talk about more next class, of a heliocentric, or in other words, sun-centered model. And really, this wasn't accepted for a long, long time after him, but we'll come to grips with why that was. There were some very significant and sensible reasons for why the ancient Greeks, by and large, did not adopt Aristarchus' heliocentric model that we'll discuss in further detail next class. All right, so in terms of what Aristarchus did, again, relatively simple mathematics. It is high school trigonometry, which I know a lot of students don't love, but the idea is that Aristarchus realized that with the phases of the moon, when the moon is in its first or third quarter, then we have a right triangle. So there's a 90-degree angle between the Earth, moon, and sun. And that means that if we can measure the angle between from the Earth here, from the sun to the moon, then we can figure out what the distance to the sun should be in terms of the distance to the moon, that is. And this is a very difficult measurement. For one thing, you have to kind of look at the sun. Ouch. And then the other thing is that because the sun is so fantastically far away, in fact, this angle is very close to 90 degrees. In other words, this angle is very, very small. And so Aristarchus measured the angle as being about 87 degrees, which gives that the sun is about 20 times as far away from the Earth as the Earth-Moon distance. And the modern value is much, much larger. The modern value is close to 390 times the Earth-Moon distance. But nevertheless, the mathematics that Aristarchus used was perfect here. And Hipparchus of Nicaea, we'll talk a little bit more about Hipparchus during the human version, but basically Hipparchus took the fact that there was a difference between the observability of an eclipse at one location in Greece compared to another location in ancient Greece, but was more of in Africa, really, like close to Egypt or modern day Egypt. And because of this change from a total eclipse to a partial, which is 100% different experience, if you've only seen a partial eclipse, you have not truly lived until you've seen a total eclipse. More on that if you take the solar system or another course. In any case, this allowed Hipparchus to use this change in the viewing angle to get much higher accuracies on the distances. And then Ptolemy will also talk a little bit more detail about in the human version of this class. But Ptolemy was, in many ways, the summation of the ancient Greek and then a little bit ancient Roman scientists. And Ptolemy came up with a very, very accurate measurement for the moon's distance as being about 60 Earth radii. I guess he did come up with 59, which is a little bit different, right, than 60.3, the modern value, but very, very close. So Ptolemy, we'll talk more about why people throw shade on Ptolemy, but Ptolemy was really a great scientist, one of the greatest scientists, in fact, from about 2,000 years ago. All right, and then in terms of improving these sun and earth size and distance measurements, we have to move fast forward 1,500 years or 1,600 years onto kind of more of the modern era. And Giovanni Cassini, who has a very nice now spacecraft from the 2000s named after him because he did a lot of interesting stuff with respect to Saturn, as well as Gene Richer, came up with a much improved estimate by looking at Mars. And this improved the estimates to the sun distance being about 364, which, still is off, but better than 10% accuracy is quite good in astronomy. Although in our solar system, we're now really, really accurate. You can see that again, some little AI isms. It decided to use LaTeX, which didn't really format properly. So of course I could have tweaked that, but since I have the human version, I decided not to. And then again, I think that this text is kind of too small. Maybe if you can see this perfectly fine, then I'm being too harsh on the AI. But we have a few other kind of fun facts related to development. One of the most important ones would be Hipparchus discovering the wobble of Earth's axis, as well as what Ptolemy found about the moon and sun varying their distances. We'll talk more about that in a few minutes. And then today we have really improvements in terms of the fundamental concept that was used to measure the distances to the sun for now 1 billion of stars. And we'll talk about this more in the human version. All right, and then I do like that the AI version has the image sources for the slide. I think that this part is kind of nice. Okay, and so now we have a little bit of a pause. So idea is to synthesize, what you learned about from the AI video, and not really just synthesize, but reflect. So I'd like you to post in the Discord. I didn't set up a particular thread for this, admittedly, but post somewhere in the Discord. And then also, very importantly, please email me just first of all what you thought of the AI version. Second, you think, you really would have liked if I had fixed up the images, etc. And, just went with the AI version instead of the human version that I'm about to show. Do you like that there's, nicer formatting as opposed to the human version? I just, by and large, stick with these white backgrounds. Although I did improve the human version a little bit since we're doing this head-to-head today. Any other complaints about the AI version? Like I was complaining here and there about the AI version. I mentioned a few compliments, but mostly complaints. Do you have any other complaints? And then, uh, so go ahead and pause and work on your answers to these items right now. Pause the video. Okay, unpause. And now, as we go through the next several slides, at some point, I'd like you to pause and give me your impressions on, like, really the comparison contrast between the AI version and this human version that we're about to go into. All right, so now we have the Very Large Telescope again. So this is a one of the projects by the European Southern Observatory. In other words, it's a project by Europe or the European Union. And we can see that there are these lasers that are shining. And these lasers are not actually just for guiding the telescope. They're using a process called adaptive optics, where basically they're creating artificial stars. There is some pretty sophisticated engineering that reshapes the mirrors at a very microscopic level, right? Because the mirrors are solid, but at a very microscopic level, you can still cause small stresses and strains, and it doesn't crack, but it still deforms the mirror with a waveform that matches the turbulence in the atmosphere to end up with very, very crisp images. And so a little bit, almost 30 years ago, now at this point, that Very Large Telescope, and by the way, so yeah, we have some very large telescopes on the ground. This is, this telescope in particular is called the Very Large Telescope. There are actually four of them, which is a little confusing. But there are four of them, and they use interferometry, which is something that you'd learn in another course, like stars and galaxies, in order to basically combine those four different telescopes to have even higher angular resolution. Okay, so we have some very large telescopes on the ground that have been put to good work and have produced fantastic images of different objects, including this very nice galaxy, NGC 1232. And now we also more recently, although Very Large Telescope is still one of the largest telescopes and it's still active, by the way, we now have really powerful telescopes up in space. Now, James Webb is actually smaller, by the way, than the Very Large Telescope, but James Webb is significantly larger than Hubble Space Telescope. And this is Lee Feinberg here, by the way. Lee Feinberg was the optical elements telescope manager for about 20 years. In other words, Lee Feinberg was one of the key persons that really tested and refined James Webb Space Telescope, making sure that the reflections off the mirror would produce the highest quality possible of images, who was given an award pretty recently, within the past few months, for really like a lifetime of service towards the James Webb Space Telescope and to NASA. All right, and in terms of James Webb Space Telescope, this is one of the most recent images. This is from 2026. This is of the so-called Helix Nebula. So admittedly not the most relevant image for this class, but still I think a absolutely tantalizing image. And it's still really, in contrast to that image of NGC 1232, which although it's fantastic and we do learn something about the distribution of stars, we don't really learn that much about galaxy evolution from this otherwise very aesthetic snapshot. For the Helix Nebula, this is a region where there's so-called galactic outflows. There's supernova explosions that are lofting material out of the galaxy. And this is a very recent area of research dating back to 2014 or so. There's still a lot of work that's being done. Only since 2020 or so did people realize that there is potentially star-forming gas in some of these outflows, not necessarily the Helix Nebula, but in different regions above the plane of our own Milky Way and nearby Magellanic Clouds. So James Webb Space Telescope. So we have some fantastic instruments today. And then, again, in contrast, going back to ancient Greek astronomy, we had really just the human eye and a couple different measuring devices. We needed to know angles, we needed to know distances. Their rulers might not have looked exactly like this, but in many ways they were quite similar, as well as quite sophisticated mechanical equipment to assist them in their observations. And the credit for the images on the slide, and by and large the material on the following slides, is due to Dennis Urkel of the Institute of Astronomy at Cambridge University. So really just eyes, simple measuring tools, and our human brains is what the ancient Greeks had. And for ourselves, we can go out, and one of the amazing things about physics, right, is that by and large, you can do these experiments yourself and understand them. If you go out to not like a parking lot where there's a ton of light pollution, but if you go out to a darker location, you can see a whole lot of stars. And one of the first things that the ancients realized is that the stars appear to move with a very particular pattern, which in the northern hemisphere is present, as well as in the southern hemisphere. Now, the Greeks were in the northern hemisphere, of course, but the Australian Aboriginals also would have witnessed this circumpolar motion. Now, what's different between the two hemispheres is in the northern hemisphere, we have Polaris, the North Star, which is very close to the North Pole. The um, the southern hemisphere was very difficult for the Europeans to navigate through in sailing ships for a long time, because there is no equivalent like bright star that is easy to identify at the South Celestial Pole. You have to basically triangulate using three different constellations to figure out approximately where the South Celestial Pole is. Anyways, the ancient Greeks noticed that there was the circumpolar motion. We obviously don't see these streaks. This is from a time-lapse photo over the course of about an hour. But nevertheless, if you stand outside and you observe the sky as the night goes on, especially if it's a nice, warmish summer day or summer night, I should say, then you'll notice that the stars rotate. In addition, and this is something that you don't have to get outside of the city lights. You can witness it, and I'm sure you have witnessed it throughout your life. At least I sure hope so. The moon goes through phases, and this is something, again, that anyone can identify. That there are periods of time when the moon appears to not show its face at all. Technically, it gets very, very, it's except for eclipses, the moon is always present, but it's so much overpowered by the sun when it's in its new phase that we typically can't see. I keep on trying, I still haven't seen it yet. And then the moon waxes through various phases to the full phase and wanes all the way back to new moon. If you were taking the solar system, I'd make you learn the phases of the moon. For this class, you will still engage with that material a little bit, but due to some of the activities, but I won't require you to know the phases of the moon for the exams. Okay, so motions of the stars. The ancient Greeks also were able to identify, that the moon went through phases, and not just the ancient Greeks, I should say, but all ancient peoples were able to observe these. And then eclipses. And this is really where things changed a little bit, where not only was there the observations of solar eclipses or of lunar eclipses are really kind of no big deal. Lunar eclipses are very reminiscent looking of the phases, although technically the structure of the blockage of light is different for lunar eclipses, where the moon is actually casting its shadow on the moon, compared to the phases where the Earth is not casting its shadow. The phases are due to partial illumination from the sun. So it has to do with viewing angle. Anyway, you'd learn more about that, and I'd really try to drill it into your heads. And Astro 100, the solar system, for these solar eclipses, they are much more fantastic. And again, you have not lived until you've seen a total solar eclipse. Next time you'd get a chance to see one in the US is not until 2044, so we're getting a little bit closer. It's only 18 years away. Um, I am saving up as much as I possibly can to go to Luxor, Egypt for 2027, which will boast the longest eclipse of the century. The eclipse in 2017, which was the so-called first Great American Eclipse at least of the new millennia, right? I witnessed that for about 90 seconds. The 2024 second Great American Eclipse, I was in Indiana, and that was about 3 minutes. I was supposed to go to Texas, but it was projected to be cloudy in Texas, so I opted to just drive as far south as I could, and just kind of kept an eye on the forecast. And again, total solar eclipses are amazing. Partial eclipses are kind of cool. It's kind of neat. It's kind of like if you checked out like a little bubbling creek for the first time. They're cute, but a total solar eclipse is more fantastic than any waterfall that I have ever seen or any mountain. They're really, really cool. So anyway, try to check one out. Again, I don't expect you all to be joining me in Luxor, Egypt, but at the very least, 18 years away, you can go to North Dakota, South Dakota, or I think Montana is the third option. Okay. And then aside from 2044 and 2045, there will be the third and last greatest, is the so-called greatest American eclipse. 2045 is the last time this century that there will be eclipse viewable across like the whole US. And by and large, the last chance to see one in, I think, our lifetimes. Maybe some of you are quite a bit younger than me, of course. Okay, and then in addition to viewing eclipses, the ancient Greeks started to notice that there are planets. And these nights, in fact, there is also a planet that is quite bright. I thought it was Venus for a while, but nope, it's Jupiter. It's up there, kind of close to Orion these days. And we won't talk too much about these constellations. You learn more about those, and they're pretty fun, but you learn more about them in Stars and Galaxies or the solar system. Okay, so now back to this progression of ideas. So we saw this with the AI version, and this part, I'll admit, is not necessarily a lot better. We've talked about how Thales of Miletus had the first mention of eclipses and possibly the first prediction. Historians debate whether Thales really predicted an eclipse or whether this was posthumously like put into Thales' mouth about the prediction part. Um, at the very least, it's very poetic about the birth of science. So I like to think that it happened, but historically, it's there's been some shade cast on whether Thales knew that the uh, moon was going to cast shade on the sun, or really cast shade on the earth, rather, or in a predictive sense or not. And then either way, the ancient Greeks talked about the planets. They're probably known, uh, decades or centuries before that, but at the very least, we have it as part of the written record, or at least oral tradition, I should say. And then we had Pythagoras, who noticed the motion of the stars and that so-called circumpolar motion, which was really that the stars that do rise in the east, and the stars that do set towards the west. And then a few decades later, Anaxagoras, again, who could be called the first physicist, gave the first correct explanation of eclipses and the idea that the moon has light not due to some god, but due to the reflection of light from the sun. And then notice that there's about 100 years here between Pythagoras and this Pythagoreans for the circular orbits. So Pythagoras was really kind of a wowing figure to the ancients. So much so, and not just a wowing figure, but Pythagoras had a really a reverence for math and a sort of philosophy of math that really approached that of a religion. And so Pythagoras had this cult following, the so-called Pythagoreans that believed in the purity of math. Anyway, so they came up with the circular orbits for planets. And then again, Aristarchus is one of the most important ancient Greek astronomers, not necessarily the most important, but really crucial in terms of coming up with one of the first quantitative measurements aside from Eratosthenes for the circumference of the Earth. Aristarchus came up with the sizes and distances for the sun and moon. And so, again, in terms of what Aristarchus did, identified that during the first or third quarter phases of the moon, there's a right triangle here. Again, the moon's phases are not due to Earth casting a shadow. The Earth would be casting a shadow along this line from the sun and Earth, but instead it's due to the viewing angle. The moon always has half of its face illuminated. Only um, in this case, only half of that half, in other words, a quarter of the full disk of the moon is illuminated. We only see the half of the moon that is closer to us. So we only see like a so-called half disk. Again, more on this in the solar system if you're interested, Astro 100. So anyway, so Aristarchus was pretty far off, but had spot on technique. And this is overlaying this now on one of these ancient Greek manuscripts, which I think is really pretty cool in terms of the diagrams that they came up with back then without computers or anything. Okay, and then in terms of kind of the next step, okay, so we've talked about how Aristarchus came up with the distance to the sun given the distance to the moon. But okay, well, what about the distance to the moon? So if we have an eclipse, excuse me, a lunar eclipse, so in other words, if the Earth blocks out some of the light from the sun that otherwise would be reflecting off the moon that we see, we have a lunar eclipse. And there are excuse me, and therefore we can compare the cross section of the Earth to the cross section of the moon because there are similar triangles here. So you can see that there is, a triangle, and then we can draw another triangle and another triangle. And because of these similar triangles, we can come up with a relationship, although it does take some math, so we won't really go over it in the lecture itself here. But we can do some math that you all will be working on in a worksheet a little bit later, that relates the radius of the Earth to the distance from the center of the Earth to the center of the moon. And so Aristarchus came up with the distance to the moon as being about 20 times the size of the Earth, whereas the correct value is about 60. So again, Aristarchus, great that came up with some quantitative predictions or quantitative estimates, pretty far off in terms of modern values, but that's okay. In this case, the effort is what we really care about. Now, a little bit later, Hipparchus of Nicaea, who, by the way, was a really pivotal, or excuse me, again, pivotal, or in other words, important ancient astronomer, not just for the sizes and distances that we really care about for this class, but relevant for stars and galaxies, and really for essentially everything that we do in astronomy, is related to the magnitude system that Hipparchus used to catalog the stars in the ancient skies. So Hipparchus cataloged the stars as being magnitude 1 for the brightest stars, magnitude 2 for the second brightest kind of class of stars, all the way through magnitude 6. And or maybe he even did magnitude 0, but I'm less confident in that. Anyway, so what we've learned is that the human eye is really a fantastic imaging device. We're actually, for people that have perfect vision, and maybe for me a decade or two ago, we're on the cusp of being able to actually witness quantum phenomena. In other words, be able to detect photon by photon. We're not quite there, but we're pretty close. I played baseball back in high school, and back then I had 25 vision, so I was probably closer to that side of things. These days, I probably should get glasses pretty soon, I'm guessing. At least reading glasses, I presume. Okay, so anyways, so Hipparchus of Nicaea, really important in terms of the magnitude system. In terms of the sizes and distances, again, use the fact that there's this difference between the eclipses. And you can see that there is the difference in the triangles that are made. So there's one angle for the triangle for a total eclipse. There's a different angle for a triangle that you could construct for partial eclipses. And therefore, due to that difference in the angle here, if you know the distance across the Earth, you can figure out what this angle is. Therefore, you can figure out what the size of the moon is really, really accurately. So Hipparchus improved substantially in terms of the distance to the moon as being about 70 Earth radii, but distance to the sun a little bit improved, but still pretty far off. Claudius Ptolemy. So again, Ptolemy was one of the most important astronomers of the ancient world, still dating back about 2,000 years ago. And the book, which is really the summation of Ptolemy's writing, this is not the title that Ptolemy gave this, but what later uh, Arabic scientists referred to it as the Almagest. In other words, which I guess technically in Arabic probably has a different pronunciation. But this Almagest is known as the greatest. It is a compilation really of all the astronomy that was known in the ancient world, which during the Arabian Golden Age of roughly 600 AD to 800 AD or 900 AD or so, the Arab nations really improved astronomy and cataloged a lot more stars. But as far as the like more, if you will, the European tradition, Ptolemy was kind of the last one before the so-called Dark Ages. So Ptolemy used that same sort of method that Hipparchus used in terms of that parallax and came up with a much better um, set of distances and sizes. And for the distance to the moon, again, this is really freaking close. The distance to the sun actually took a little bit of a step backwards. Um, and in terms of Ptolemy, um, again, two really key things that Ptolemy came up with was the fact that the distance to the moon actually varied. And one thing to keep in mind is that in the ancient world, although they, were starting to develop mathematics, right? Starting with Pythagoras, really, and the Pythagorean theorem. Keep in mind that before Pythagoras, no one knew how to figure out the distance for different sides of right triangles. They didn't have a formula. For Ptolemy, and for really until around 1600 AD, there was no mathematics for ellipses. So this distance variation for the moon, as well as the distance variation for the sun, which to our eyes means naturally that, oh, that means that the orbits are ellipses, this was a huge puzzle. And Ptolemy was the one that came up with a really, I'd say, sophisticated and ingenious solution of using circles upon circles to come up with the orbits. And we'll talk about that more next time and relate to one of your activities for um, the lecture number 4, or really your week 3 lecture. And so again, Ptolemy was a really important scientist. Now, people cast shade on Ptolemy because the Almagest is not just the culmination of astronomy, but the culmination of astrology. And Ptolemy intimately linked the two. Ptolemy was both an astronomer and an astrologer. Ptolemy thought that if a child was born with Mars in a certain location in the sky, or other celestial alignments, that there were monsters that were going to be born, and you'd have to stone the child to death, or really like the newborn infant. So really like kind of terrifying stuff. As you can tell, I'm not a fan really of astrology. Maybe I'll lighten up at some point, but overall, so Ptolemy, great scientist, also unfortunately um, kind of the forefather of that branch of pseudoscience now known today as astrology. It can be fun, I guess. So if you're into astrology, that's perfectly okay, as long as you understand that, it's kind of celestial navel gazing, right? Okay, so moving on. Um, Cassini and Richer. So this time we have, the image, since we're not relying on the AI. So Cassini and Richer, basically did the same thing as Hipparchus and then Ptolemy did, but were able to use telescopes and therefore did the parallax angle for Mars, and that really helped to better constrain distances in the solar system, and they came up with really not a distance to the moon in this case, but helped constrain the distance to the sun to within 10% of the modern value. Okay, and then in terms of astronomy today, we use the same technique called parallax, which we'll become more intimately familiar with next class. But we use the same technique today. The idea is that if we wait 6 months for the Earth to go around the sun, then there can be a small apparent deviation in the position of a star. And that tells us, if we know the distance between the Earth and the sun, about how far away that star is. And this is a crucial item for this course. So we will talk about parallax more in the future. But as far as your quiz 2, and possibly also your quiz 3, parallax is important. You're going to need to know what parallax is, okay? All right. So in terms of astronomy today, so again, this Gaia satellite, which unfortunately just ran out of steam. It was retired in March 2025. Over the course of about 10 years, this Gaia satellite cataloged the positions and to really high astrometric precision, the distances to about 2 billion stars in our Milky Way galaxy, using this exact same principle of trigonometric parallax. The next mission to be kind of like Gaia is planned for the 2040s, and unfortunately, we can't do parallax to anything really beyond our Milky Way, or to some extent beyond Andromeda. So in terms of the next level up, we're not actually doing anything in terms of more distant galaxies. The plan for Gaia NIR is basically to take a look at all the same objects again and see how much they've shifted, and that should help us better constrain dark matter, which is nice, as well as a variety of other properties. In terms of looking also at variations in light, we might be able to detect like 1 billion exoplanets, which would be a huge boon. But more on that if you're interested in Astro 100, or I'm actually teaching a summer course about that, but that's not with Purdue University. Okay, so now this is the end of today's lecture, and now it's really your turn. So we're going to do an activity, and I didn't actually set up a separate thread for this, but please, as you're working on this Aristarchus Sun and Moon worksheet, ask for help and ideally also offer help. The idea is to spend roughly 30 to 60 minutes on this Aristarchus Sun and Moon worksheet. This whole lecture was about an hour. Now, admittedly, I did have a couple of pauses for you to do other mini activities, so maybe shoot closer to 30 minutes. Again, the goal is about 2.5 hours total in terms of viewing this lecture recording, as well as responding to the icebreakers or different activities, handling the Eratosthenes worksheet, as well as this Aristarchus Sun and Moon worksheet. So the idea is basically to come up with your own distances to the sun and moon. And I think that this is a pretty fun activity. It's some students do find it challenging. So what I'd like you to do is to email me how long it takes you to complete the worksheet, or if you spend your remainder of the 2.5 hours working on the worksheet, how far you got within that time interval, however long that may be. All right, so I hope that you all enjoyed our Class 3 lecture, and stay tuned. I plan to have the Class 4 lecture posted much more rapidly in Class 3, since I already have that partially created and I get to leverage a little bit of material from the solar system and other courses that I've taught. So have a good night, have a great week, and stay tuned for week 3 and beyond. All right, bye bye.